If you can't do that, how can you answer the quiz?
I know, good question.
He's asking the
Is
question.
that not too dark? Okay, let's get some hammering. So welcome everyone, this is the annual quiz night. It's about having some fun. Multi-choice questions, there's loads of chocolates to be dished out. And it's rather than question, move on, question, move on. The questions are fun, but they're also just a vehicle to pluck one point out of one of the topics discussed and expand a little bit on that. So it's a fairly relaxed night. So let's move on. Okay, so these are some of the key topics we talked about. Cratering, it was the 50th anniversary of the first moon landing, so it's a little bit about that. We're going to measure a bit about the stars. We talked about the solar neutrinos. We introduced the Hertsprung-Russell diagram, the colour magnitude diagram, and we talked about large ground-based telescopes, and then we did part one of space telescopes. So those are the main sort of topics going to be covered. It doesn't matter whether you have talks or not, it's all stands on its own. Okay, so question one, cratering, aging the surface. Does this topographic map of Mars suggest, and I'll ask this shortly, but have a look through those. One, the northern hemisphere surface is older than the southern, or the northern hemisphere surface is younger than the southern, but both of similar ages. You can't draw any conclusions. Oh, sorry, I wasn't understanding. So that's the Mars topographic map. You can see there that's it wraps right around the globe. That's the northern hemisphere, and the southern is called a dichotomy. You might read of the Martian surface dichotomy. One side is thicker, the southern hemisphere is thicker than the northern. Probably from a large collision or something early on in the solar system. Okay, everyone's made up their minds. What do you think? Yep.
The answer?
Oh, yeah, well, let's have a look. So, the answer was B, yeah. Who got B right? Oh, loads of people. Yeah, one over there too. Yes, one there, that's it guys, okay. Two chocolates. Two chocolates. Maximum 2 chocolates. Funny thing was, I bought a stack of these, and one of my, I put them in my office at home, and one of the packets accidentally broke open. So you can't have loose chocolates. So I ran, for my sins, here I am, what, 8:58, and I got a zit. Not like I was 18 years. Anyway, the principle here is that craters are used to date surfaces. They give you some indications. And you count that when astronomers, planetary scientists look at a surface like this, they're interested in counting the numbers of craters, the density of craters, and the size of craters. And from there they can work out how old, roughly, a surface is of a planet and compare it. And you'll notice here the northern hemisphere, that's relatively low. As the topographic maps usually blue means with lowland. It's mainly smooth, relatively recent lava flows. Just a few craters dotted here and there. Now look at this. These are the southern highlands. There's just craters everywhere. Some huge big impact basins going on here. And that tells you that it's an older surface. So let's click on here. Now, the point of this graph is to graph things out. Graph A is the diameters of craters here. And for here, you've got the frequency, or in other words, how often you see craters. I've just chosen here 1 giga-year, which is 1 billion years. And you see, bottom line is that over that time, there are more frequent, small craters are far more frequent than large craters. So here's the frequency here, and these small craters here, 10 to the minus 2 meters. There's zillions of them. I was going to say buggers, but I'll be more technical than that. Zillions of them up here, sitting up here, and there's much, much less of these large craters. So that's for 1 billion years. You can draw that graph nicely. Graph B, you're looking at the age of the surface and you're mapping that against the frequency. So this automatically tells you for an epoch that craters get less frequent with time. In other words, if you see loads and loads and loads and loads of craters, it's more indicative of an older surface. If you see very, very few craters, it tends to be younger. The logic being is that geological processes come along and wipe over a surface and create a new surface and wipe out most of the craters. And the point of this graph brings it both together. It correlates with different epochs. So they've got 1 million year here, So the surfaces that are 1 million years old, and you can draw a nice little plot like that that shows this principle quite nicely with the size of crater diameters here and the frequency of craters. And that correlates quite nicely in a sort of fairly nice pattern there. The bottom line is from all of that is craters tend to get smaller and less frequent with time. So a young surface is just going to have a few craters, relatively small. An older surface is going to have loads and loads, much more craters, because they just haven't been altered by geological forces. And you say, well, what's the large bit all about? And we'll come to that shortly. But here's time for another question. So they could tell you, you could tell from there which surface was older than the other one. But okay, how do they actually put a figure on it? That surface there, for example, is 2 billion years old. That one is about 3.5 billion years. So how are crater counts calibrated? There's a clue there. Who can tell me that one? What's just tell me in 2 words. Yeah, absolutely, Bill. Yeah, but in particular, meteorite. Where did that rock come from? No, that's not a meteorite. Radiometric dating is
Crystal's the answer?
Come on.
Crystal volcano.
Apollo moon landings. That's moon rock. Okay, so what the astronauts did, of course, there were 5 successful landings on the moon. Six successful moon landings. And they went to different regions of the moon each time. They brought rocks back. The rocks were radiometrically dated fairly accurately. They still continue to do that with more and more accuracy. But they correlated the rocks with the lunar regions and did countercrate, from the satellite images, did of the numbers, the frequency, and the size of the craters, and correlated that with radioactive, and it just came out beautifully. So that's how they now look at the surface of the planet, and all things being equal, they'll tell you because of this work, and Apollo astronauts' work, they'll tell you sort of with a rough guideline of how old that surface is. Yeah, back to the question, okay, so why the big craters when they're older? The general idea is that early days of the solar system, the planets all formed, of course that was all chaos, but then the planets formed, but there was still a lot of smaller bodies in the outer solar system. There was a time early on when a lot of the planets were still formed, but they were still a bit molten, or just this little crust had formed and so on around them. The bigger planets all migrated out, and with the laws of conservation of angular momentum, all these huge influx of all these small bodies, solar system small bodies, all headed inwards and started smashing into the inner planets. And it's called the late heavy bombardment period. Late heavy in terms of it was pretty full on, but late as opposed to the early period, of course, when the planets were first forming. And that's, of course, the rocks were much bigger in those days, so the craters were bigger. And slowly with time, the bigger and bigger rocks slowly got consumed up by smashing into planetary surfaces. So with time, when they got used up, of course, the material hitting the planets got less and less frequent and smaller. So that explains why when you see lots of large craters, it's an old surface. You see just a few small craters, that old surface is being wiped over by a geological force, usually lava or something like that, or oceans, and you just left with small meteorites and so on. So that's the idea behind craters. So learn from a lot from the surface just by looking at craters. Size of craters, numbers of craters, and the density of craters. Okay, question 2, the Apollo moon landings. Everyone loves the Lunar Rover. So here it is here. What Apollo missions used the Lunar Rover? Apollo 12, 14, and 15?
No. 14, 15, 16, and 17? 15, 16, and 17? Or 14, 16, 17? Or sorry, I'm sorry. C. Yep, okay. So, all right. Who's got me? All
right, here's your last chocolate. It's your last one.
We'll see. We'll see.
He's Italian. He keeps saying C.
We'll see about that, okay?
Who else? C, sure.
Thank you, Chris. He's going to get pimples.
Okay. So let's talk a little bit about the Lunar Rover. It's a cool piece of equipment. So there it is there. It was used on Apollo 15, 16 and 17, the last 3 missions. And remember the main theme of that talk was that everyone's recalling Apollo 11 and with a lot of fanfare and stuff, but a lot of people don't realise there were 5 other successful landings. and with each consecutive landing, the ante went up, the length of time they spent on the surface went up, the technology and instruments laid on the moon went up, the amount of rocks, they brought it back, at the end of the day they brought back about 3 or 4 times the amount of rocks per mission than when Apollo 11 brought back. So the ante just went up and up. But one of the great things, these last 3 missions, they were able to use the Lunar Rover, so to start travelling longer distance to do geology, had electric motors on all 4 wheels. Here are the wheels there, they're made from aluminium and zinc, and good old tractor chevron style treads made from titanium. That's it. Now why are the wheels made from aluminium and zinc, metal? Why not have some rubber tyres? Burn some tyre, do some burnout something. Why not? The heat, yeah. That was useful, wasn't it? The heat. Oh, you're right, sir. Good catch. Yeah, the heat, you can't have rubber tyres up there, they're going to go bang and burst and so on. It's the heat's too much.
Could they have used rubber tyres on the dark side of the moon with no sun or not?
There's no shade. You're winding me up. There's no shade. Right, chocolate back. Come on. I'm calling in the chocolate. No, because you have the water race an interesting question. You said the dark side of the moon. And a lot of people do use the term dark side of the moon, but there is no dark side.
Yeah. There's no sun.
Well, there is.
Yeah, there is.
Yes, for the night time, yeah, there's no permanent dark side of the moon.
Could you use rubber there?
Sorry?
Could you use rubber where the sun's not shining on the moon?
Yeah, well, the temperatures do, but yes, you could. If you wanted to be, it'd be pretty dangerous though, you can't see what you're doing. You need lights and stuff to do it. But you've raised some good talking points.
You couldn't, because when it's dark, it's absolutely
Exactly, temperature extremes.
There's another job.
I like your thinking. There's your last chocolate,
It's the point Niven mentioned is the weight, because I imagine rubber tyres will be a lot heavier than
Because they have
those
these
things.
solid rubber tyres, because you couldn't rely on air pressure.
Yeah. Being American, Michelin tyres. But also, at the time of day, it works out a good point there too, is that the moon rotates every 28 days. So a lunar day is 14 Earth days, and a lunar night is 14 Earth nights. So you're going to be in the dark for a long, long time. But the astronauts prefer to land at 10 a.m. moon time. So in other words, what we would imagine sort of early to mid-morning here. The logic then is shadows. It's cooler, the sun's up high enough, but there's shadows. So when you're coming into land, you can't judge distances on the moon. There's no atmosphere. How do we judge distances? We look at how hazy something distance might be. You might see it next to a tree or a house, but there's no visual cues, and there's no atmosphere on the moon. So it's hard to judge distances. So part of what they used to help land was they were following the shadows of the lunar modules that came in. That gave them a good clue. So they had the sun behind them at an angle of about 10 degrees, about 10 a.m. Some of those longer missions, these 3 missions here, they didn't leave the moon until about 1, 2 p.m. lunar time. And I think it was David Scott from Apollo 15 commander commented how the heat was so bad his watch was melting into his suit on the last day. So that's the extremes, no doubt.
Kill time.
Now the top speed, about 18 k's an hour, that was done in Apollo 17, that was the record. The range was no, it could do more, but they didn't want to go much more than 36 kilometres. I think they only went to a total of 28 kilometres. Who can tell me for a chocolate why, despite it could go up to 36k, it actually never went further than about 28 kilometres away from the lunar module? Yeah, okay. All right, free. Everyone knew that one, so there you go, guys. Here's the chocolate.
Broken tooth.
Another one out there somewhere, finally. So, yeah, exactly. There's no point in hopping in the lunar module and heading out 36 kilometres and suddenly it breaks down and it's a 4-hour walk back to the lunar module. Hello, Nick. Houston, we have a problem. I've only got 2 hours of oxygen left. So if you only had 2 or 3 hours of oxygen left in your suit, you never drove away such that the lunar rover broke down, you're within your walking distance back, walking time back to the lunar module. So that's that constraint. Yes, Tony.
I understand that because they left the parking fine at this is now greater than the original cost of all of those moon missions. And also over the moon, parking, leaving illegal.
It was Auckland Council, I'm sure.
Send a compliance officer up there now.
Oh, let's do this,
Apollo 13, the astronauts, of course, had to use the Lunar rover, the Lunar module rather, to pilot and never get themselves back to Earth. And is it Grumman who made the Lunar module? Yeah. And they sent the bill to, now who made it? Was it Boeing or someone who made it? Yeah. So normally the Boeing service module would have brought them back. But of course, they'd clapped out to work to bail Grumman's Lunar module. So Grumman sent a bill to Boeing, a towing fee. Something like about 370,000 kilometre towing fee. So it's good to see them have some fun. And part of the Apollo 11 talk that we did on the moon, it was just, I sort of unashamedly sort of said, look, I've got these pictures just to enjoy because we've got a big screen here. And so that's a nice panoramic view that Neil Armstrong took. That's the eagle there. And you just see it's one of the craters, the East Crater. But these are views often that you don't see in a book, so I just grabbed some nice big wide panoramic pictures just to put up here and get a nice little view. So that's the iconic picture there of Buzz Aldrin, of course. That's him there, at least known one, just assembling some equipment. This picture I put at nice high definition. This one came out recently, only this year got touched up. Increased resolution. But you see here that Buzz Aldrin, you probably see, but look closely here, he's turning around and looking at the camera. Well, if the spacesuit's not hugging to your face, you're not looking around like that. Yeah, it's big and roomy in the helmet, and he was looking around like that. So, so they've pumped this picture up and they've increased the resolution to make it more obvious. So you don't often see that. That's one of the few pictures of Neil Armstrong. We gave the camera briefly to Buzz to take some pictures. It's one of the very few you'll see of Neil Armstrong on the moon. Just getting something out of the equipment bay. That's just a quick one, of course, blowing up. I mean, fuzzy that I just couldn't help myself. But let's just put it on and enjoy that. So that's Neil Armstrong. That's another great picture. That's Neil Armstrong. When he first went onto the moon, he got within the first sort of 10 minutes or so, taken by Buzz through the window. He's got his visor up. Most of all the pictures of the astronauts have got the gold visor down to protect your eyes. So he was sort of reading in the shadow of the lunar module, and he had his visor up so you can actually see Neil Armstrong's face. So that's not a picture you commonly see. It's got a cool picture after the moonwalk, and that mankind is how it is done. So pretty elated, no doubt. They hadn't slept probably for a day or two, but they were just hyped up on adrenaline. So it's after the moonwalk. That's Gene Cernan, commander of Apollo 17, the last man on the moon. I put that in here just to, it showed there was nothing glamorous about going to the moon and stuff. It's just covered in grime and moon dust. It just stuck everywhere. And they were concerned about how it would get into the electronics and so on. I think at the talk I recounted the story how when the lunar module came back up again to the command module, they linked up. They didn't want all the lunar dust and stuff floating through the command module that might upset the delicate instruments. So they set up a little gradient of air running from the command module into the lunar module. So astronauts had to brush themselves off. They brushed themselves off on the surface of the moon before they mounted up into the lunar module. They took turns and brushed each other down. When they got in the lunar module, they had a further brush down. And then before they went to the command module, they had another little bit of a brush down. But it adhered to everything. But they had a little air current flowing through from the command module to the lunar module when they had linked up, just to prevent all that dust and grime. And that will be a problem when they go back. The new Artemis suit and stuff is designed around that. That would be a good thing to put. I have got a bit of
A Dyson vacuum cleaner now.
They need a Dyson V11 up there, don't they? Yeah. So, question 3, measuring up stars. How do they measure the temperatures of stars? So this is Sirius, the dog star. It's in the sky at the moment. It's coming up nice in the evening sky, and that's Sirius there. So the astronomers tell us Sirius A, it's a double star. There's Sirius B there, it's a little white dwarf. But Sirius A, surface temperature, if you look it up in Wikipedia or wherever, dare I say, 10,000 degrees Kelvin. Well, how do they know? Do they go up there and stick a thermometer in it, or what?
So let's find out how they actually tell. So the surface temperature of stars is measured by parallax, photoometry, spectroscopy, astrometry. Sorry, I wasn't listening that much. Who said C nearby? Oh, I was going to say, you go, Rex. The gentleman just, oh, that's John there. And someone over that way. I know. Did you get it? Who got E? Come on, yes. Okay, so checking a star's temperatures, introduce you to the spectroscope. Spectroscope, crudely put here as an instrument, there are little slits of the light come through, hits a prism or some grating, and essentially it splits the light up into all its individual wavelengths, which comes here, that's sort of on the focal point here, focal plane. So it splits light up to different wavelengths, and that's what it looks like here on the CCD photographic sort of platal image, and you can see all the individual lines, fine little lines, all representing the different wavelengths of light. Dark refers to that light's coming, all the light is coming from the star, but it has to pass through the atmosphere of that star to get to us. And there's various atoms and elements and stuff of various states of energy levels sitting in the atmosphere. When the light comes from the sun or the star, those molecules and atoms and elements and so on absorb the little photons of light at specific wavelengths. So where you see a dark patch, that means more light. Something in the atmosphere of that star has absorbed more light in that particular wavelength. So that's the pattern we tend to get. If you put that onto a tracing, you get a little tracing there of all the different wavelengths. But look, there's big dips that correspond. So here's your intensity, here's all the different wavelengths and angstroms, and there's your intensity. So if you plot that on a graph, see where it's darker, something's absorbing it, so you get a little dip on the graph, a big dip there, a little fuzz there, all the little lines in there. And that essentially tells you what molecules or elements, atoms of different energy levels are lurking in the atmosphere of that star that absorb the light burning up from inside the star. So that's called a spectroscope. Does that. And then you get a computer and you plot yourself what we call a spectral energy distribution graph, whereby here's all your wavelengths again, here's your intensities. That last one was just a short space, but this time they've spread it over the whole lot. The set goes up, lots of dips, lots of ups and downs, then big dip here, and so on. It peaks here, starts going down, and the general. So you see a trend going on? Up there, and back down that way, with lots of little dips on the inside. So that's called a spectral energy distribution graph. And that's what, when you put all that data through the computer, what it spits out for you. So, okay, so you get all that, but still, okay, how do you measure the temperature from that? Let me introduce you to the concept of blackbody radiation. Stars are considered to be black bodies. So what's a black body? A black body is something that tends to shine any light on it. It doesn't reflect light away. It absorbs all the light, such that the only light that's being emitted from that black body, is light that's indicative of the thermal energy, how fast all the atoms and molecules and elements and so on, how fast they're moving around, how hot they are. As opposed to, for example, you hold this up, you say that's not a black body, because most of the light you're seeing on this is like being reflected off it, not really, you need probably an infrared to actually see that, or a microwave to see the thermal energy coming off that. So a black body is something that the energy you're seeing coming off it is pretty much, for practical purposes, it's all there's a thermal energy. The body is not reflecting any light. So that's called a black body. And stars are considered close enough to be black bodies. So they call this a Planck curve, and this is an SED, spectral energy distribution, of what's called black body radiation, a perfect black body. And once again, you've seen that picture set goes up, like that, see the general pattern, what we saw in the last slide, comes up and it comes back down again. And if you have a look here, they've mapped out how hot something is, the surface of a black body, and you can, with theory, with equations, you can actually then plot what it would look like. The surface of a body that's got a surface temperature of 4,000 K will start rising, and will peak at about here, at about sort of, you know, say 1200, sorry, 800 angstroms and so on. But you notice the pattern here, the hotter a body is, that peak in wavelength is getting more intense, and it's been shifted to the higher energetic, to the shorter wavelengths as well. And so that's the main principle. And then a guy called Wien created Wien's law, whereby the maximal wavelength, in other words, this peak here, the maximal wavelength with an equation 0.0029 divided by, and that figure there is your temperature. So if you know that, you do your spectroscopy, you tell your computer to spit out a spectral energy distribution, you have a look at it, you work out what's the peak wavelength, what that correlates to, plug that into the equation, that tells you roughly how hot it is. But there's more in that picture. Look here. So here's your peak here. Your peak, you looked at from Sirius A was about sort of 4,500 angstroms or so, and that, you put that to the equation, that correlates to about 10,000 degrees Kelvin. At those degrees, you don't have to worry about Kelvin versus Celsius, forget about it. It's all the same at those 35 degrees. But there's a little bit more to it. So that gives you a roughly crude idea of the temperature, but you can refine it a bit more. All these little dips here that tell you, there's sort of their fingerprints. What wavelengths they are and the pattern they are, they all correlate to specific elements, specific atoms, in specific energy states. So you analyse all where these dips are as well, and you can tell what elements are in the atoms and so on are in this atmosphere of that star, but what energy states are they missing 1 electron, 2 electrons, and 3, and so on. And that further reflects the energy levels that are going on in the atmosphere against that star, and that defines your temperature. So that's how you tell what temperature to start. So a spectroscope, then your telescope, map one of these out, find out and give me your peak. Your peak is of your wavelength, and then have a look at these things as well.
Yeah, Chris, they do use photometry for estimating stellar temperature, multicolour filters, and the difference between the intensity in two different colours.
Which
that's used as an approximation quite often.
yeah, and then which are going to come with colour index and stuff too. Yeah, which I'm going to come to. But yeah, so this is just a very, this is your basic method, but yeah, there's a bit more to it. Ooh, what's going on here? So, solar neutrinos. We did a talk on solar neutrinos. It was all about the bottom line is what energizes the sun, what powers the sun. The sun is powered by Kelvin-Helmholtz contraction, nuclear fusion of hydrogen into helium, nuclear fusion of helium into carbon, nuclear fission of uranium 235. Or sorry, I didn't pay attention at this. Who said E? A bunch of liars. Okay, so anyone who hasn't had a chocolate has got 3% B and hasn't already had a chocolate.
You said it.
Andrew? Oh, here you go. Oh, yeah. Haven't got a chocolate and you said B. Here you go. Got it. Oh, you get the chocolate.
Was it?
Okay. I've lost my here it is. Here it is. Okay, yeah, absolutely. It's nuclear fusion of hydrogen and helium. And they, with the 1930s, with nuclear physics and stuff, they soon worked out that was the most likely cause of it, but they had to prove it. And their equations showed them that that was going on in the right amounts as their calculations had said. They should be detecting these little tiny little subatomic particles, very elusive, called solar neutrinos. And they did indeed, well, they detected these solar neutrinos, but they suddenly realised there was a third as many as there should be. And the bottom line is the Sudbury Neutrino Observatory in Canada then did some really cool experiments and discovered that actually neutrinos were 3 different flavours. They through superposition, they change the different flavours and the way the sun to the Earth. So that's in a nutshell why I spoke about that. So I thought I'd grab the concept of fusion hydrogen into helium for the talk. Kelvin-Helmholtz contraction, that's probably a little bit in the theory does go on. That refers to if you get a body, it's yay big, and it starts contracting down through the release of gravitational energy that emits heat. And stars in their early stages before the hot enough for nuclear fusion kept in your cores, that is the main way that they emit energy. It's through just contraction, and they glow because of that Helmholtz contraction. Of course, fusion of helium into carbon occurs later on in stars when they've used all their hydrogen up, and the helium that's often part of the next stage. Of course, nuclear fusion, that's good for doing that on Earth, and lots of contamination. And I'll forget the Okay, so let's look about what happens with nuclear fusion. So you've got, the bottom line is Long's equations and pathways, but let's just cut into the chase. You get 4 subatomic particles called protons, positively charged. You can get 4 of them, shove them together to create 2 protons, and 2 protons also turn to neutrons, so you get sort of 4 subatomic particles. But the difference in energy is there's a difference in mass. The mass of this is actually much, well, is significantly greater than this. And this is where Einstein's equation come in, E equals mc squared. In other words, m is the mass, the difference between mass, this and this and this. There is a difference in the mass. You multiply that by the speed of light, which is a very, very large number, which you square, and that gives you the energy that gets released in the process. So in the process of combining 4 protons of a certain mass to create 2 protons and 2 neutrons, which is helium, 4 subatomic particles joined together, there's less mass tied up in here, and it's released as energy, and that's what fuels the sun. That's nuclear fusion. So that's what's going on in there.
We must be missing something though, Chris, because the neutrons slightly heavier than the protons.
I think that you'll find the mass between them.
When they're in a bound state, the total mass is less.
Yeah.
Correct.
When you do all these calculations, what to do with Swinburne and stuff, you have to get them in the individual states, the atomic mass.
Right.
And there is a difference. There is a difference. Give us your chocolate back. Spit it up.
The neutron is heavier, but that's only because it's measured in isolation.
Okay. So the bottom line is here. So you think, well, these guys here are all positive, and I'm led to believe they're pretty strong forces. I've been told that equal forces, equal charges repel, absolutely. So you try and get 4 protons together, what happens is eventually they all click together, and that's called the strong nuclear force. But between them sitting here and stuck together, the strong nuclear force is very short range, very potent, but very short range. So you try and get these protons and bring them together, but the closer they get, it's like bringing 2 magnets together that are repelling equal poles. So you get so far, and the repulsion force goes up and up and up and up and up and up. You're struggling to get them. And then if you can manage to get them together, bang, they could. And that's what's going on here. But the math says that that's not an easy thing to do. It's not an easy thing to get, such that. So you're going to need. So what your problem? How are you going to overcome these repulsive forces? What's the key to it in the sun? How the sun is able to go such a significant way getting these protons together despite their increasing electromagnetic repulsion.
Temperature.
Yeah, who said that? That was Keith. The safety officer from a nuclear plant. Fair dinkum. Here you go.
We've been trying to do it for years,
Okay, yeah, exactly. It's pressure and temperature. The temperature at the core of the sun is 15 million degrees. You know, and as we talked about during the year, temperature is a reflection of how fast things are moving, the kinetic energy. 15 million degrees, huge pressures as well. That's how the sun is able to achieve it. Well, maybe. So, is this enough? The classical, and here's your core here at 15 million degrees. All the protons have been ringed together and so on, and hopefully joining up to form helium. And then you get these high energy photons get formed. Just the talking point, they take up to 1 million years to zigzag the way of the sun, and of course just 8 minutes to convert from there. But is the 15 million degrees Kelvin, is it high enough? Well, the classical laws of physics is no, it's close, but it's not enough to overcome that increasing repulsive force till you close enough where bang, then strong nuclear force kicks in. So, what else is required? One last factor. Yeah, that's Tony and Bill's in there. Quantum tunneling. Let's talk about quantum tunneling. Have you had a trouble?
I had one.
You've only had one.
Yeah,
I don't want to be the only one in the room with it.
yeah. Somebody had a sort of just an explanation with the sun. If you follow the one proton around, it's obviously colliding with other protons, millions of them per second kind of thing. On average, before two protons stick together and form deuterium,
Yep.
which is the first step of that reaction, the average time is about 1 billion years.
Yep,
That's
exactly.
why the sun burns for so long, essentially.
Which,
If the reaction happened really fast, the sun would just blow up and we'd be vaporized.
which comes to hold, yeah, exactly. So Bill's point was we're going to talk about. So what quantum physics means, that the laws of classic physics is if you want this rock to end up over here, you've got a big hill, which this hill is representative of the repulsion, electrostatic repulsion. You've got to work hard, you know, pull it up, and down again. The laws of classic physics is that pressure and temperature analogy of someone looking at rocket is not high enough. You only get it to about here. So that's classical physics. But the theory of quantum physics says that where anything is at any one time, it's only a probability. You don't know for certain. For example, I've got this holder here in my hand. If I threw it at a certain angle, a certain amount, classical laws of physics says it's going to land right there, and that's it. End of story. Let's move on. Get over yourself. It's going to land right there. Quantum physics would say no. Probably 99.8% chance, 99.9% chance it's going to be here. We'll give you that, but there is a millionth of a chance. It could be over there. There could be a zillionth chance. It could be there. There could be one chance in a trillion. It could be over here. It could be over here. It could be there. It's a probability pattern. We agree. It's like a 99.9. We'll give it to you. It is probably going to end up there, but it's not a done deal. It could end up somewhere else. And you do those calculations, and there is about a 1 in a zillionth chance, let's make it figure out, you get my point, a very, very, very tiny chance that that rock could suddenly just appear there on the other side of the Mercury, or on the other side of that repulsion. So they've been jammed together, 15 million degrees is not enough strong enough. But the laws of quantum physics is there's nothing stopping one in a zillion protons just suddenly ping appearing over here. It's already there. You know, they're joined together. And that, they know that exact figure. I just use 1 in a zillion just figuratively. But as Bill was saying to that, they do the calculations, they know, and it matches the mass of the sun versus the energy up to the sun perfectly. So not only does quantum physics sort of explain all this, but this testing and the finding these solar neutrinos which proved that there was hydrogen fusion to helium going on in the sun, but also that was a great success for proving a bit of quantum physics as well. Often people, oh, quantum physics is too airy theory and stuff. But no, it's for real, and quantum tunneling explains it beautifully, mathematically, to the right proportions. So that was the point there of solar neutrinos, that the sun is powered by the core